right, this is sort of a section that's going to move us beyond the kinds of numbers we've been working with. The numbers we've been working with so far have been rational numbers. They've been numbers where we can write them as a fraction of integers. So we can write whole numbers on top and bottom, and there may or may not be a negative involved. Okay? We're going to move a little bit beyond that in this section. And the first thing I want to talk to you about is a description of what real numbers look like. And the first thing I'm going to do is I'm going to draw a really large rectangle. And inside of my rectangle are all of my real numbers. Okay, so everybody with me so far? All right, the next thing I want to do is I want to sort of subdivide this rectangle into two pieces. The way that I'm going to draw my subdivision is not supposed to be indicating like how many of them are in each side or anything like that. I just need more space on one side to write than the other one. Okay, so my division is not in any way, shape, or form to scale. Okay, so don't misunderstand that. But I am going to divide this up into two pieces. We'll do it right here so I don't write my words. Okay, on the left-hand side, I have numbers that are called irrational. And on the right-hand side, I have numbers that are called rational. Two different things. They do not intersect or meet in any way, shape, or form. They're either rational or irrational. Okay? Every number you know in your universe is one or the other. Okay? Every real number you know is one or the other. Say that. Okay. So within the rational numbers, though, there is more that we can break them down into. So I'm going to do all my breaking down of all these things, and then I'm going to go back and give you some numbers to describe them in each category, okay? Rational numbers can be broken down further into several different types of numbers. The first breaking down is integers. So everything inside this rectangle is an integer. And then we can break it down a little bit further than that. Inside of the integers rectangle is a rectangle called whole numbers. We're going to do it one more time. Inside of whole numbers, we have the natural numbers. Any other divisions of numbers that are standard divisions of numbers, and we can always talk about things like even versus odd and stuff like that, but these are the natural breakdowns of the different number systems within real numbers. Okay? We're actually going to start in the innermost square because when children are really young, that's where they start. When you first learn to count, what number do you start counting with? 1. And then you go 1, 1.5. No, you don't, right? You go 1 and then 2 and then 3, and those are called the natural numbers. They also are sometimes called the counting numbers. Okay, so these numbers inside here are numbers like 1, 2, 3, and so forth. Okay, and then somewhere in either kindergarten or first grade, a child learns, formally, they learn addition and subtraction. And when they do, they run into some kind of a problem that looks like 3 minus 3. And if it's 3 minus 3, we don't have a number inside of my square right now that would work. We need a number 0, right? Once we introduce 0 into our world, we have what are called the whole numbers. So the whole numbers are 0, and then 1, 2, and 3, and so forth. So it's 0 plus everything in the box before it, okay? And then somebody does some cruel trick, like my husband did my daughter the other day, and he said, well, what's 27 minus 28? She's in 3rd grade. They haven't done anything like that yet. Can you imagine? I don't know exactly when you run into this, but I definitely think it's not that young. But at some point, you do run into this idea, right? You run into the fact that you need something that's negative to represent some things, right? And we use negative numbers in real life all the time. You just don't think of them that way. One of the most common places that you use negative numbers is when you talk about debt, right? This was the borrowing money kind of issue that we had in the last section, yeah? So you borrowed money to go to school, or you borrowed money to buy that car, you borrowed money to whatever, then that means you actually have a negative amount of money. Agree? You have money you owe. So negative numbers are going to be my integers, and we're talking about negative whole numbers, so it's all the whole numbers we had before, so we still have the 0, 1, 2, and so forth, but we go the other direction on sort of the number line as well. Okay, so we go both directions, all the whole numbers, positive and negative. And we've talked about integers already because we described rational numbers that way back in chapter 6 for the first time. So rational numbers took my integers. Okay, so the integers are inside the rational numbers. That means that all of the integers, all the whole numbers, all the natural numbers, all of those are rational. Okay? But we introduced the concept of having things like fractions and decimals. Okay? That's along the lines of about 4th grade or so that you run into that. And so you have numbers like, and I can't write them all, right? But you have numbers like 3/4 and negative 4.6, etc. Now, you also have not just that, but you have like non-terminating decimals like we did in 7.3, right? You have something like 0.62 repeating. So all your repeating decimals, all your terminating decimals, all of your fractions, whole numbers, natural numbers, all of that is rational. So what kind of numbers have I not described? Square roots. That's what I sort of left out of your description. And so you run into square roots, I don't even know, maybe junior high, maybe 6th grade. I'm not exactly sure where that hits. But at some point in late elementary school or early junior high, you run into the idea of square roots. And so you need things like square root 2. And it's not all square roots, right? I mean, like square root 4 wouldn't go over here. Why not? Because if it's simplified, and its simplified form looks like the number 2, and 2 is rational. So it isn't all square roots, but it would be the unsimplifiable square roots, right? There's also another number you run into over here that you've seen in classes before. It's definitely elementary school, and that number's pi. Yeah? You've seen the number pi. Pi is also irrational. There's no way to write the number pi as a fraction, an exact fraction. I mean, we write a representation, 22/7. We write a decimal, 3.14, but those are just approximations. Those are not the real value for pi, right? There's another one that you run into somewhere in high school or college if you take certain courses. That number's e. If you haven't run into it, don't worry about it, but e is about 2.718, but e is irrational as well. And it's actually defined in calculus finally where it comes from, but it's introduced before you get to calculus. So e is one of these numbers. So thinking about radicals, you're thinking about pi, you're thinking about e. Those are the kinds of numbers that are irrational. And that's actually the numbers we're going to be taking a look at in this section in particular, are the irrational type. Because we did rational numbers. That was chapters 6 and 7. Those were all about rational numbers. All right, so irrational numbers. Here's some description of how those are defined, I guess, how they're determined. There must be an infinite number of non-zero digits to the right of the decimal place. Okay, so the numbers on the right-hand side, we have infinitely many of them, and there's no repeat in it. So we have infinitely many of them with repeating decimals too, but there's no portion that repeats. Okay, those are irrational numbers. And one of those irrational number concepts come apart with square roots, as you guys already described. And for example, a real common one is a principal square root. So principal square roots are defined in the following way. So if a is a non-negative number, then the principal square root of a is denoted square root a, and it's the non-negative square root of a. So let's actually do a and b here to describe what the difference is. So you see example 1, it says find the square roots of 121 and find the principal square root of 121. So what was that? You would. So do you know what the number is going to be? It is 11. 11 times 11 is 121. So on the first part, Audrey says you should have a positive 11 and a negative 11, and that's correct. And the reason is because 11 squared is 121, but negative 11 squared is also 121, right? So when we take a square root, we actually have a positive square root and a negative square root. However, when you see that square root notation, it doesn't mean square root. We say that. We say, what's the square root of 121? What it means is what's the principal square root of 121. So when you already see the square root written down, if you've got a problem that's already written like that, it's actually saying what is the principal square root of 121. It doesn't say what is the square root of 121. We're terribly lazy sometimes in the mathematics world. We just abbreviate things, right? We abbreviate with symbols. We abbreviate in our notation. We abbreviate in our language. So you, all the time, all the way along until you probably heard me say it right now, you've looked at that and said, what is the square root of 121, right? That's not really what that says. That says what is the principal square root of 121. And what is the principal square root of 121? It's 11. The principal square root is the positive value. And that's the definition that we see written right here. Making sense? We're doing okay? All right, so it isn't just square roots, right? It's actually nth roots. So we can do any index. Okay, so this number right here is called the index, this little n. Okay, that's an index. And whatever the index is tells you how many of the item underneath the radical that you're looking for. Right? So when we did square roots, we were looking for two numbers, because it was a square root, that multiplied together to give you 121. Agreed? Okay. But on this one, you've got a 4, yeah? So you're looking for one number that you multiply by itself 4 times to get to 625. So the easiest way to handle any of these is to factor them. You can factor them with a factor tree, or you can factor them with the graduated factor form, which I think I showed you here, didn't I? Okay. So we'll do a factor tree here because I haven't done one in class, but what's some number, any number you like that would divide 625? 5 works. Yeah, so 5. We could go with 25. 25 times what? Do you know? 25. It is. It's 25 times 25. That's right, Anna. All right, it's 25 times 25. We're not done, though. We aren't done until we get it in primes, and 25 is not prime. So 25 will factor, and so both my 25s will factor, and they will each factor into 5s, right? So I can actually rewrite this as the 4th root of 5 times 5 times 5 times 5. And how many 5s are there? There's 4 of them. And that's what we needed, right? We needed 4 of them. And there's 4 of them. So what we're asked to find then is how many groups of 4 of the same number are there, and there's one group of 5. So this answer is simply 5. Okay? So when I do this, I sort of think to myself like this. This is the language that's running in my head. I think the number on the outside tells me how many items I need to circle. So I circle 4 items. They're all the same number. Once I circle those 4 items, this comes out 1 time. Because I'm canceling those 4 items with the number 4. And I get one of those numbers on the outside. It's easier to see when you actually end up with something left underneath. And I think I do in the next one. So let's take a look. Yeah, I do. Okay, so the directions say write each of the numbers. The value underneath the radical is as small as possible and still an integer. Okay, so in other words, factor completely and finish. Right? Finish this up, factor completely. So 363. I'll do a factor tree on this one too, and then I'll do the other way on the other one. What is 363 to this y? Something unique. So this is what, 3. And if you divide it by 3, what do you get? 121. 3 is prime, but 121 isn't. In fact, you've seen 121 today, haven't we, Madison? Yes, we have. What is 121's factoring? 11 and 11, so that's nice. So what I literally have underneath this radical is 3 times 11 times 11. They're Everybody with me? Yeah, okay, great. What's the index for this problem? It's a 2. Remember, index is the number that's right here. And if there isn't a visible number right there, it's what you always say when you say it. You say square root. It's an understood 2, right? So there's an index of 2. If it helps you to see that, to remind yourself, put it in. Because that number tells you how many you have to circle in a group. So I circle my group of 2 11s. I have my 2 11s that I then bring out once. So I've got 11 on the outside, and then I've got my square root, but the 3 stays underneath. Any questions on that one? Okay. B. What's my index? 5. 5, okay. So I'm going to be factoring this one a while if I think there should be something from that, all right? So let me do my my factor up, my quotient up, division, description. This is 320. What is the smallest number that goes into 320? 2. Okay, so what's 320 divided by 2? 160. What's the smallest number that goes into 160? 2. That's 80. Smallest that goes into 80? 2, and that's 40. The smallest that goes into 40? 2, and that's smallest that goes into 20? Oh goodness, that's 10. We're almost done. Smallest that goes into 10? 2, and that's 5. And we're finally done. How many 2's was that? A lot, I agree. 5th root of how many 2's? There are 6 of them. And 5. So, there's a bunch of 2's. There's at least 5 2's. Yeah. So how many 2's do I need to circle? 5 of them. That's what the index tells me. So I circle 5 of my 2's. And those 5 2's will come out as one single 2 on the outside. Then I have a 5th root. There's a 2 still underneath and a 5 still underneath, which means the total underneath is 10. Okay, any questions on this one before I move on? Okay. Pythagoras. You've heard of this guy. Or at least you've heard of his name associated with this theorem right here, a squared plus b squared equals c squared, right? I don't remember what year it was. I should look it up. I could probably find it if I just Googled it. But years and years ago, Shaquille O'Neal, Shaq, on the Jay Leno show. I think it was. I think it was Leno. And he talked about the things that smart people know. And one of the things he said was the Pythagorean theorem. You know the Pythagorean theorem, then Shaq has now said that you were thus smart. Okay? The Pythagorean theorem is actually credited, at least with its name, to a philosopher named Pythagoras. Pythagoras was Greek, and he actually wasn't the first one who knew about it. The Mayans and the ones who say the world's coming to the end soon. Are you guys all ready for that?
When is it supposed to be?
2012, and we're there, so.
I don't remember what month everybody freaks out.
I don't know.
It's December 23rd, but
December 23rd. Okay.
or like 21st or something. But I would basically said that the calendar just moves over, and it doesn't really.
Oh, well, so we're okay. Well, if you're not ready, you better get ready because it may come to an end. Of course, it could really come to an end anytime, right? Of course. All right, so the Mayans actually knew about the Pythagorean theorem. That's what we call it right now. Before Pythagoras did much, much earlier. But the interesting thing about Pythagoras is that he actually, he more or less had a cult, okay? So he was a philosopher, and back in the day, the philosophers had, people who followed as disciples, right? And they were their teachers and these sorts of things. And Jewish history is like that as well, right? You have the Pharisees and you have the Jewish leaders, and they had, people who followed them, not in a sort of sacrilegious way, but they were their teachers, right? So this is sort of what was happening. But they had a commune, it was, they lived there like the monks and those kinds of things. This is what's happening. And they studied philosophy, and mathematics is part of philosophy. And so they studied mathematics. And one of the things that they wanted and believed and felt like should be true is they felt like it should be true that every number was able to be measured. So in other words, like you should take a tape measure, right, or the equivalent thereof, and find me a closed decimal or fractional sort of way to represent every number. Okay? In other words, what they wanted to not be true is for square roots to be possible. That's the essence of what that means. Okay? If everything is measurable, able to be measured, then we have no need for these non-repeating, non-terminating decimals. Which is what irrational numbers are. Well, the problem is that very quickly, if you take, in fact, I'll just draw it because my square number ends up looking like a square on here anyway. If you take, oh, that doesn't look so good. A square, so by definition, a square has length 1 on each side. A square has the same length on each side, so we'll call it length 1. And you find the diagonal of that square. Well, you find the diagonal of that square using right triangles. Agreed? You guys see the right triangle? Yeah. Okay, and that right triangle has this property associated with it. Okay? And there's lots of ways to show that this is true with lots of cool mathematics stuff, and we may do that if we have time at the end of this semester, because it is really cool. And it's really simple to show the Pythagorean theorem works, okay? Without a lot of mathematics. So, but it does. We've got 1 squared plus 1 squared then equals c squared, because I have hypotenuse, the longest side to side opposite the right angle is c. So what's 1 squared? 1, so I've got 1 plus 1. So what's 1 plus 1? 2. And now I've got c squared equal to 2. And the problem is that if you use just known decimals, okay, there's no decimal that you have that when you multiply it by itself, you get exactly the number 2. I'm terminating this. Okay. So this very simple unit square shows that irrational numbers exist. And Pythagoras didn't like that very much, so while he gets credit for this theorem, what he really did was he hid the theorem. He didn't want anybody else to know about it, so it's a big secret, right? And he gets the credit. This is an interesting character, Pythagoras. But the Pythagorean theorem is relatively easy to use, okay? There are some things you have to sort of be careful of as you work. But those things that you have to be careful of as you work, if you're careful, they're easy to avoid, okay? So one of the first things that doesn't matter for your knowledge is where A and B are, okay? A and B are the sides of the triangle, or the legs of the triangle. They're the pieces that are perpendicular to each other. So we can say that A is X, or we can say that A is 3. It doesn't make any difference. So just put them in there somewhere. But it matters that C is the side opposite the right angle. Okay, so that's the one that matters. You've got to make sure that C is opposite your right angle. And then we can set up with the Pythagorean theorem. So Pythagorean theorem is a squared plus b squared equals c squared. And if we use the a and b like I wrote, again, it doesn't matter that we do, what would this look like? Right, that's what it looks like. Okay? All right, so x squared is x squared. What's 3 squared? 9. Here's the nuance that you have to be careful of over here. This squared applies both to the 2 and to the square root 3. Right? So this means we've got to square the 2 and we've got to square the square root 3. We've got to do it to both. Now you can't distribute squares over addition or subtraction. But, oh, I wrote 3, I'm sorry. Yeah. Thanks, Sarah. Oh. When you don't put things down on a smartboard, it keeps using the same operation. Erase. All right, so what's the thing? Okay, so you can't do this to addition or subtraction, but you can distribute exponents over multiplication. That is a property of exponents. So what is 2 squared? 4. And what is square root of 3 squared? 3. So we actually end up with a 12 on the right, yeah? Now what? Subtract my 9. So I have x squared on the left, what's on the right? 3. And then what is x? Square root of 3. So to undo the square, we square root. And we're not working with square roots because these are all distances, right? So we're working with principal square roots. Your distance can't have negative square root. That's a negative number. We're not negative, negative. There's no negative distances like that, okay? All right, so I have one example problem of how we can use this. Are you ready? I think. Let's see what it says. All right, here's an example of radicals. Jose. Jose says that the equation square root negative x equals 3 has no solution because the square root of a negative number does not exist. You've probably heard that phrase before. Why is the argument incorrect? So inherent in the way it's asked, it says that the argument is incorrect, doesn't it? Yeah, that's part of what the directions are actually telling you from the get-go. So, but part of what he said has some truth to it, doesn't it? Yeah, I mean, part of what he says, this business of square root of a negative number does not exist, that's a true statement. But somehow that's not applying to what's going on then, right? Because that statement is actually accurate, right? Square root of negative 25 doesn't work because 5 times 5 is 25, and negative 5 times negative 5 is 25. There's nothing that gives me a negative 25. So what's wrong with his argument? Okay, so let me write what I think you're saying. So if x itself is negative, then negative x would be, and you use the language something like negative 1 times x, right? And would then be positive. Does that sound right, Sarah? Okay. Which gives us positive underneath the square root, right? If we did this. In particular, what number for x would work here? Negative 5. Not quite. Negative 9 would. Yeah. So in particular, we'll actually solve it for him, and I'll show you how you could actually solve it too, just not just look at it. But in particular, if x equals negative 9, then the square root of negative times negative 9 equals 3 and solves the equation. Is that all right? Yes. Right. So here's the difference on how we use which one, okay? Whenever the radical is already in the problem, that means principal square root, okay? So you've probably had some teacher had to do something along the way, and I actually know what happened when we went through the square roots and algebra course. And they said something like this. They said, if you put the square root in the problem, you have to put a plus or minus with it. But if the square root was already there, it means positive square root. It means the principal square root. So the location where you would see something like that, it looks like this. If you had y squared equal 9, and you put this square root into it, then you would say that this is y equals 3 and negative 3. So you're forced to solve. Right. And even as I say that, I sort of hesitate. Here's why. In this section, the primary thing you're going to see is Pythagorean theorem, which means you put square roots in. But you have to remember what your variables are representing here, right? They're representing distances. And so, again, even though you're putting the square root in, you're only going to get the positive one of it because you're talking about a distance. So you're not going to encounter that plus or minus very often in this section. But if you did, it would be under this kind of context, or it would be under the context of the language. It would say something like in that first example, what are the square roots of in the number, as opposed to what is the principal square root of in the number. Now, I wanted to show you one other thing before I stop this particular slide, and that's how you would actually solve this if it was potentially like a number that wasn't so clean or easy to see, or maybe you just don't see it even right now as you look at this one. So if you were given and you wanted to decide is Jose right or not, you would take this problem and you could actually try and solve it. Okay, so ignore whether he's right or wrong just to see what happens. How to get rid of square root? You square both sides, right? So we'll square both sides. On the left-hand side, that leaves me with negative x. And on the right-hand side, that leaves me with 3 squared is 9. And then how do you move the negative? Multiply by negative 1 or divide by negative 1. Yeah? And so you get x is equal to negative 9. And then if you weren't sure if it would work, you could, of course, try it and see. And we already did that part, so I won't show that again. But if you get that answer and it doesn't work, when you try and plug it back in, it's going to be readily obvious it's not going to work. Is there any questions on that kind of concept? It's a little strange, right? Because we don't like seeing the negative underneath the square root. Obviously, Jose didn't either. Right? He readily said something's wrong. And if we had a negative, 3 underneath the square root, or a negative 2, or a negative 57, or whatever, we should have red flags. We're saying, I can't do square roots of negative numbers. And that's true. Problem is, x isn't a number, it's a variable, which means it can take on anything. And in particular, if it takes on the number negative 9,